Hello and welcome in this chapter about sets. Today, we will see the basics. Let's start with a definition. A set is a collection of objects. You can think about a bag, and you can put whatever you want in it. It can be numbers, it can be words, people, anything. For example, A is the set made up of 4 elements, 1, 2, 3, and 4. B is a set made up of 3 elements, water, fire, and air. Pay attention. A set is not a list. It is determined by its elements and not by a particular order. It's like a bag. You can shake it, it will remain the same set. Moreover, you will not have several identical elements. You want to know if fire is in your set, not how many fire you have in it. Let's have a few notations. If an object X belongs to A, we write this way. X belongs to A. It is equivalent to say that X is an element of A. In the other hand, if X is not, we write the same sign but slashed, like this. You can read this, X does not belong to A. Let's take an example. Here, blue belongs to A, but green does not. That's for notations. It is really important to distinguish between elements and sets. Here, for example, X is an element. It is a variable, it can take values. But this is the set whose only element is X. It cannot take values, it is a set. We can go on as far as we want. Here is the set whose only element is the set, whose only element is the set, whose only element is the set, whose only element is X. Be sure you always know at what level you are. It can be quite confusing sometimes. Now, the number of elements in a set has a name, cardinality. We write it in between vertical bars, like the absolute value. Let's take a couple of examples. A has 4 elements, so we write that the cardinality of A is 4. The same for B with 3. Now, what about the set of even numbers? Well, we have to count even numbers, so C has a cardinality of plus infinity. There are 3 main ways to describe a set. Depending on the context, some are more appropriate, and you can usually switch between them. The first is what we mostly did so far, namely listing all the elements between squiggly brackets. For instance, I can write that A is the set made up of 0, 1, 2, and 42. It's a perfect set. But now imagine that I want all the integers from 1 up to 42. I could write everything, but it would be quite long. I could also use what we call a set roster or dots. If I write this, you understand what I mean by dots. You can use dots to let your sequence go endlessly, and of course you can use any sequence you like, as long as your pattern is clear. If it is not, maybe you should use our second way. This way is the most common one. The idea is to start from a number field, like real numbers, positive numbers, rational numbers, what you want, and to select elements having a certain property. This is called the property necessary for membership. Every element of your starting field that satisfies this property will be accepted as a member of your new set. Let's take an example. Here, our starting set is R for real numbers. You read this part as every X in R so that X is in between 1 and 4 and X is an integer. The vertical bar here means so that. Note that we could write this set 1, 2, 3, 4. It is equivalent. Using a property necessary for membership is also called using a set builder. You can build every set with this as long as you have one starting set and one refining property. We could imagine another set, which will be the set of all English words that starts with a W. And we will read B is the set of every English word so that their first letter is W. Our third way is more graphical. It is using Venn diagram. Basically, you're just drawing something close to a circle and you fill it with elements. With Venn diagrams, conventions are not really strict. You can fill it with whatever you want as long as we understand what you mean. However, they are really useful to visually express relations between sets. You have all seen this kind of diagrams where 2 sets share something and have each something apart. In this case, the set of letters of Latin alphabet and the set of blue things have a blue A in common. This representation will be really useful when we will discuss operations on sets. So to sum up, We can write every element in the set or interpolate with dots. We can start from a broad set and select the members we want, or we can describe it visually with a Venn diagram. Just a few words about a very particular set, the empty one. Of course, you could write it just with squiggly brackets, with nothing in. But it also has its particular notation. It's a /0 or /O. About the empty set, we can say that its cardinality is 0. It is the smallest set you could ever have, and it is unique. There is only one set with no element in it, and it is the empty set. This is sometimes useful. Now we enter the last part of this video, and we will begin to play with more than one set. We will see how sets can be related to each other. Let's start with inclusion. Given two sets A and B, we say that A is a subset of B if and only if for every element X in A, X is also in B. You can also say that all the elements of A are elements of B. We note it with this sign: A is a subset of B. Visually with Venn diagrams, this is quite clear. You see that all the elements in A are automatically in B. Or whenever you take an element in A, then you know that it is in B. If it is not the case, then you say that A is not a subset of B, and you denote it with a / inclusion sign. It means that A has at least one element that is not in B. For instance, the first set is a subset of the second one, because 12, 9, and 0 are all three in the second one. But here, 3 is not in the second set, so the first set is not a subset of the second one. Now, another relation between two sets is equality. It is quite intuitive. We say that A and B are equal if and only if they have the same elements. We write it with an equal sign. A equal B means that whenever X is in A, then X is an element of B, and whenever X belongs to B, then it belongs to A. If it is not, then we will write it with a non-equal sign, A non-equal to B. For example, the set it is raining is equal to raining it is, and also equal to is it raining. This is because the order in which the elements are listed does not matter. Just a remark, two sets A and B are equal if and only if A is a subset of B and B is a subset of A. This is very useful in mathematical proofs. If you have to prove that A and B are equal, then you can prove that A is a subset of B and B is a subset of A, and this is often easier than checking all the elements. Last but not least, there is a special case when you know that A is a subset of B, and you also know that they are not equal. Then you will say that A is a proper subset of B, and you will write it this way. By that we mean that whenever X is an element of A, then it is an element of B, but there are elements of B that are not elements of A. You can see it as a strict inclusion, and as before, if it is not the case, we write that A is not a proper subset of B this way. For example, it is raining is a proper subset of it is raining man. That's it for the basics. Thank you for your attention.